I know there are more pressing things on many of your minds, but we do have some new chemistry to talk about. So we're gonna finish chapter 4 today. We're talking about molecular orbital theory is what we started last time. We're gonna see some more details about that and finish this off. So last time we talked about molecular orbital theory. We introduced it for just the s orbitals. So things like hydrogen or helium, when they form bonds, the s orbitals interact, they mix to form two different molecular orbitals. We saw that one of those was a sigma orbital, which is bonding, and then we had the sigma star antibonding orbital. So only two energy levels. We can fill those with electrons. Now, as we get into the p block elements, things become more complicated. And in general, molecular orbital theory is a more complex theory, so we're not going to go beyond anything more difficult than diatomic elements. Just two atoms bonded together is as complicated as we're going to get for this. But we do need to talk about the p block, which has some additional layers of complexity to it. So if we mix together p orbitals, p atomic orbitals, to make molecular orbitals, we're going to assume that the bond axis is in the x direction. This is what your book does, although it's not the most conventional way to do it. But we'll assume that the bond axis is x on the Cartesian coordinates, just so we can keep everything straight. And so then when we mix together p orbitals, just like we saw for valence bond theory, there are two types of interactions that can happen. We have sigma and pi in this case. So the sigma p molecular orbitals are the first ones. So in this case, we're going to do an additive combination of two p orbitals. So if we take two p orbitals that are along the bond axis and then combine them, we can form sigma molecular orbitals. So these are going to be the px orbitals. Remember that there's three p orbitals, px, py, and pz. And if we mix the px orbitals together, we can get a bonding molecular orbital, where again what we want to think about here is that these are delocalized orbitals. So we have our individual atoms with their p orbitals. We mix them together to form a diatomic, and we get these delocalized orbitals where we have this overlap in the middle, but we're thinking of it as one delocalized orbital. So the p orbitals mathematically combine, and you get this region of electron density in between the nuclei that's responsible for the sigma bond. Now again, this is very similar to the picture we drew for valence bond theory, but remember that valence bond theory assumes that there are two individual p orbitals that are overlapping. For molecular orbital theory, we're mixing them together to form one combined delocalized orbital that's delocalized over the entire molecule. We no longer have separate p orbitals involved in that bonding. Okay, and then if we do the antibonding combinations, remember that for molecular orbital theory we have bonding, which is the in phase, and we have antibonding combination, which is out of phase. We would call that sigma star. And that's going to be a subtractive or out of phase combination of two px orbitals. So remember that if we do an out-of-phase or subtractive combination, we invert the phase of one of our orbitals. So we can think about flipping this over, and then when they combine, you're going to have the opposite phases overlapping, and that's going to give you then a node. So you're going to have something that looks like this. Where you have a node in the center between the two nuclei. All right, so you no longer have positive overlap between the nuclei. You have the electron density is outside the nuclear region, and then that's going to be an antibonding interaction, which would weaken the bond if that was filled. So those are the sigma p molecular orbitals, very similar to the sigma s. It's just they have a slightly different shape because they're derived from p orbitals instead of s orbitals. But then p orbitals can also form pi molecular orbitals. And we sort of saw this when we introduced valence bond theory, the idea of pi interactions. So these pi p molecular orbitals, again, come from in-phase and out-of-phase combination of p orbitals. This time they're going to be along another direction, a perpendicular direction, let's say py. So if the y direction is the vertical direction here, let's assume that. We're going to take two py orbitals we're going to do an in-phase combination to form a pi p molecular orbital. All right, so again, if we want to draw the nuclei in red, just to keep track of them, where they are. Nucleus at the center of each of these atomic orbitals, and then they combine to form molecular orbitals, and we get this overlap above and below the bond axis. But again, we want to think about it as we're forming a delocalized molecular orbital, one orbital that's delocalized over the entire molecule, not two separate p orbitals anymore. So you get sort of this overlap above and below, but it's in-phase constructive overlap, so it is a bonding interaction. And then if we do the pi star p orbitals, the antibonding combination, that's going to be out of phase, py minus py. And again, when we do an out-of-phase combination, we can think of it as we're inverting the phase of one of the orbitals. So we're flipping this one over, for example, and now we no longer have the like phases overlapping, and so you get you have your bond axis here, and you're going to get the opposite phases aligning, and so you get, again, a node in between the nuclei. So this would be an anti-bonding interaction. So again, a delocalized orbital that's delocalized over the entire molecule, but it's anti-bonding in this case. So those are the PYs, and then we also have the same exact thing happening in the Z direction, which I'm not going to draw up, but the Z direction would be sort of coming out at you. So these same pi interactions occur in the other coordinate as well. So when we mix p orbitals, we're going to get two degenerate pi p and two degenerate pi star p orbitals. All right, so to make that more clear, this pi p orbital has another copy of itself that's just rotated 90 degrees and is at the exact same energy. And this pi star p orbital, which I guess I didn't finish labeling, that one has another copy which is also just rotated 90 degrees but exactly at the same energy. So when we make the pi orbitals for using p atomic orbitals, we're going to get two degenerate orbitals at each level. All right, so if we draw the diagram for this, it's obviously more complicated, but here's what it looks like. And now we do have a slight difference here. So we're going to start out with O2, F2, and neon 2. So if you're in sort of the second half of the P block, so this would be, O2 is P4, this is P5, P6, those three elements, when they form diatomics, here's what the molecular orbital diagram looks like. So the valence orbitals for these guys is going to be 2s and 2p. So we have to mix both of those sets of valence orbitals together to make molecular orbitals. So just as we saw last time, when we mix s orbitals together, if we take our two s atomic orbitals and we do mathematical linear combinations to make molecular orbitals, we get a bonding sigma 2s and an anti-bonding sigma star 2s. So same exact interactions that can occur with 2s orbitals. We're not changing that part of the picture. And then if we go to the 2p level, so we have three degenerate 2p orbitals for each atom, and they're going to mix together to form molecular orbitals. And as I just showed you, those p orbitals can mix together to form pi or sigma molecular orbitals. Now, one thing we talked about when we first introduced molecular orbital theory, or maybe I didn't talk about it, I don't remember, but anyway, if I didn't talk about it, it's important, is that the energy splitting for these orbitals, remember that the bonding orbitals are always lower in energy, the anti-bonding orbitals are higher, but how far apart they are in energy depends on how strong the overlap is between the two orbitals. So sigma is a much more direct head-to-head overlap, so in a conventional sense you're going to get a larger splitting for the sigma levels. So the sigma bonding orbital for the 2p's is going to come down lower in energy. The sigma star 2p is going to go up higher in energy. You get a larger splitting for the sigmas because it's a more direct head-to-head overlap. And that influences then the energy spacing of the orbitals. Calculating the energy of these orbitals comes from quantum mechanics, so it's not something we're going to talk about in detail. But in a qualitative sense, when you split the levels, sigma is going to have a larger splitting than pi because of the more direct overlap. And then the other ones are going to form these pi molecular orbitals. And remember, as I said, for each pi I should probably put these labels to the side. They're a little bit crowded here. So these are going to be, this is going to be our bonding pi 2p. So again, the bonding combination is lower in energy, and then the anti-bonding pi star is going to be higher in energy. Okay? And as I said, we get two degenerate orbitals at each pi level. So you have the py and the pz that combine to form a degenerate set of pi 2p and a degenerate set of pi star 2p orbitals. So this is the orbital diagram for O2, F2, and neon 2. You have your sigma 2s at the bottom, sigma star 2s, and then you have your sigma 2p, pi 2p, pi star 2p, sigma star 2p. So the most important thing for you to sort of remember and to learn is the order in which these orbitals come in, because that's going to be the order that we fill them when we start adding electrons. It's helpful to also understand where they come from and how we mix the atomic orbitals to get them. But as long as you can know the ordering of these orbitals, that's going to allow you then to answer the vast majority of the questions we give you on homework assignments and tests. So if we want to put electrons into there, we have to figure out how many valence electrons does O2 have, and we count those just exactly the same as we would when we were doing Lewis structures. So each oxygen is an S2P4 valence configuration, so each oxygen has 6 valence electrons, so that means in total we have 12 for O2. Okay, so we're counting valence electrons the same way, and then we're going to add those valence electrons to these molecular orbitals, again following the Aufbau principle, filling lowest to highest, and following Hund's rule when that's appropriate. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then the last 2 electrons we go 11, 12. So remember that Hund's rule tells us if we have degenerate orbitals, we fill them one at a time with the same spin before pairing them up. So those last 2 electrons are going to go up here, both with the same spin, both in separate orbitals. And this is, again, sort of one of the crowning achievements of molecular orbital theory. When we first started talking about this last time, I told you guys that O2 is paramagnetic, it has unpaired electrons, and this orbital diagram correctly predicts that, which we would not get from just drawing a Lewis structure or following valence bond theory. So molecular orbital theory predicts that O2 is paramagnetic, which is what we observe. All right, so this represents then an improvement over the previous bonding theories because an experimentally determined phenomenon was explained correctly by the theory. So remember, that's what the scientific method allows us to do. If there's something that the theory doesn't perfectly explain, we refine the theory. And this molecular orbital, this delocalized bonding theory, correctly predicts that O2 is paramagnetic. We can calculate the bond order for this. So we would predict from valence bond theory that O2 is a double bond. So if we just drew the Lewis structure, we would get this. And let's see if the bond order from molecular orbital theory matches that. So remember that the bond order, we take 1/2 and then we multiply it by the difference between the number of bonding electrons and the anti-bonding electrons. So the bonding electrons are all of those that are in bonding orbitals. So we have 2 here, 4, 6, 8. So 8 of our 12 electrons are in bonding orbitals. 2, 4, 6, 8. And then the rest of the other 4 electrons are in anti-bonding orbitals that have stars by them. So we have 2 here in the sigma star 2s, and then we have 2 up here in the pi star 2p. So a total of 4 electrons that are in anti-bonding orbitals. So 1/2 times 8 minus 4 is 2. So the bond order is predicted to be the same as what we would expect from valence bond theory. And so that doesn't really change, that picture doesn't change when we move to molecular orbital theory. So in general, molecular orbital theory will give you the same bond order that you would get from valence bond theory, but it does predict the paramagnetism. And then finally, if we want to write the electron configuration for O2, so remember that we write these configurations just like we do for atomic configurations, where we start with the lowest energy orbitals first, we add the electrons, and so what we get is, from this diagram, sigma 2s has 2 electrons in it. Then our sigma star 2s also has 2 electrons. Then we come to sigma 2p, which is filled. We have pi 2p, which has a total of 4 electrons. We just write that as one orbital level, a degenerate set of pi orbitals. And then our pi star 2p has 2 electrons in it. So this would be the correct way to write the electron configuration for O2, which comes then from this diagram as we fill the orbital's lowest energy to highest energy. All right, so again, the most important thing for you to be able to do is to remember the ordering of these orbitals so that we can add the correct number of electrons to them and then start making predictions about the bond order and the number of unpaired electrons and anything else that we ask you related to that. All right, so that's the story for O2, F2, and Ne2. So let's just do the last of these as well. It's going to be a little bit repetitive, but it'll give us some good practice. So if we're talking about F2 now, we have the exact same diagram. So in S2, the two s orbitals mix to form sigma and sigma star. The two p orbitals mix to form, again, the sigma 2p, pi 2p, pi star 2p, and sigma star 2p. So we're forming the exact same set of orbitals because we have the same valence orbitals here, 2s and 2p. And then the only difference between this diagram and the previous one is that F2 has more electrons. So F2, each of them has 7 valence electrons, so a total of 14 for this one. So we're just going to add 14 electrons to this diagram, lowest energy to highest energy. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. All right, so we put in the 14 orbitals, or sorry, 14 electrons like that. So we get a sigma 2s2, sigma star 2s2, sigma 2p2, pi 2p4, pi star 2p4 configuration. It's predicted to be diamagnetic, so all the electrons are paired in this case, and that's what we observe experimentally for F2. I think I spelled that wrong. Diamagnetic. All right, it's diamagnetic, and then we also can predict the bond order as well. So 1/2, the number of electrons that are in bonding orbitals is still 8. We have 2 down here, 4, 6, 8. So 8 of our 14 electrons are in bonding orbitals, and then now we have the remaining 6 are antibonding. So 2 in sigma star 2s, and then 4 in the pi star 2p. So we have a total of 6 antibonding electrons. And so when we calculate the bond order, we get 1. So this has a single bond as opposed to a double bond. And that's exactly what we would predict from valence bond theory as well. All right, so this orbital diagram allows us to predict a diamagnetic molecule with a bond order of 1. And then let's go then to the last neutral molecule in this series, so Ne2, neon 2. Now we know from the properties of noble gases that they don't like to form bonds with each other or with really much of anything. So let's see if molecular orbital theory predicts that a bond will be formed when we interact two neon atoms together. So neon 2 has the exact same diagram. 2s mixing to form sigma and sigma star. And then our 2p mixes together to form sigma, pi, pi star, and sigma star. All right, in this case we have 2 neons. Each one has 8 valence electrons, S2p6. So we're going to need to put 16 total electrons into this diagram. And what we see then is we have 8 total orbitals, so they're all going to be filled. Okay, so we fill all of the orbitals in this diagram with 16 electrons, 2, 4, 6, 8, 10, 12, 14, 16. 16 total electrons. So if we calculate the bond order for this, we have 8 of those 16 electrons are in bonding orbitals, 2, 4, 6, 8. The other 8 are all in anti-bonding orbitals, 2, 4, 6, 8. So we get a bond order of 0. And again, as I told you last time, when we predict a bond order of 0, that means that this molecule is unstable or just simply doesn't exist. All right, so molecular orbital theory predicts that 2 neon atoms will not form a stable bond. Question? All right, so what those numbers mean is the first number is the number of electrons that are in bonding orbitals. So bonding orbitals are the ones that are lower in energy or not labeled with a star. So you have 2 electrons here in this bonding orbital, you have 2 in this bonding orbital, and then you have a total of 4 in the pi 2p. So 8 of those electrons are in bonding orbitals, and then the other 8 are in anti-bonding orbitals. And as you subtract those two, multiply the difference by 1/2, and that gives you bond order, which is going to be 0 in this case. And when you have a 0 bond order, it means the molecule just doesn't exist. All right, so we predict that neon 2 is unstable. and we of course we don't observe it experimentally either. So it's not really necessary to write the configuration for this because it's a molecule that doesn't exist, but in molecular orbital theory predicts that for us. Now the part of this that gets a little bit confusing is when we go to the first half of the p block. So this is something we're going to have to remember. It doesn't change the predicted bond order if we forget to do this, but it does change the predicted number of unpaired electrons. So when you go to the first half of the p block, B2, C2, and N2, P1, P2, and P3, what happens is two of the orbitals switch their order, okay? So the 2s orbitals mix in exactly the same way to give us sigma and sigma star. But when the 2p orbitals mix together, our pi 2p is actually the one that's going to be lower in energy, and then the sigma 2p. All right, so the pi and the sigma 2p's switch their ordering, and then the antibonding ones stay the same. You get the pi star and the sigma star. So the only difference with this diagram compared to the last ones is that these two orbitals here switch their order. And again, that's going to be for B2, C2, N2, the P1 through P3 members of the P block. All right. Now the reasons for that are a little bit complicated, so I don't expect you to necessarily understand it fully. But basically, what happens is that in these atoms here, the s and the p orbitals, the atomic orbitals, are closer together in energy. And remember what I said: when orbitals are close together in energy, they can mix together. And so you actually get some mixing between s and p orbitals as well, which I'm not really explicitly showing in this diagram. But because of that mixing of the s and p, that's what results in these orbitals flipping energy. So it's basically the 2s also contributes to the sigma 2p, and it sort of pushes it up in energy a little bit. So that's why it happens. We don't need to really understand that. We just need to remember that the ordering of these switches. And like I said, it won't change the bond order that you predict, but it will change the number of unpaired electrons and the types of bonds that are predicted. All right, so if we add the electrons for B2, we'll do that one first. B2 has a total of 6 valence electrons. Each boron is an S2P1 valence configuration. So now we're going to put 6 electrons into this diagram, going from lowest energy to highest energy. So we go 1, 2, 3, 4, 5, and 6. Okay, so again, we predict we have 2 unpaired electrons. So it's a paramagnetic compound. We can predict the bond order using the exact same equation. Nothing changes with our bond order prediction. So it's 1/2. The number of electrons that are in bonding orbitals, we have 2 down here in the sigma 2s, and we have 2 up here in the pi 2p. So we have 4 electrons that are in bonding orbitals. The other 2, the sigma star 2s electrons, are anti-bonding, so 4 minus 2. So we predict a single bond, a bond order of 1. And the configuration is going to be sigma 2s, 2, sigma star 2s, 2, pi 2p2. Right, so each of those first 3 levels has 2 electrons each. Now here's the part that's weird about B2, which is something that we would never predict from valence bond theory. So when we introduced valence bond theory in hybridization, we said if you have a single bond, it's going to be a sigma bond. But if we look at the bonding in this molecule here, the sigma 2s and the sigma star 2s cancel out, so we have no net sigma bond, and the only filled bonding orbital is going to be then this pi 2p. So we have a single bond, but it's predicted to be a pi bond. That's something we would never predict from valence bond theory. All right, so that's another little weird wrinkle that this molecular orbital theory introduces, which is the possibility that even if you have a bond order of 1, you can still have a pi bond. It doesn't have to be a sigma bond, as we would predict from valence bond theory. Okay, so this predicts a single bond order, a single bond, but a pi bond and not a sigma. Okay, and again, that comes from the fact that our sigma 2s and our sigma star 2s cancel each other out, so there's no net sigma bond, and the only net bond that we have then would be the pi, because this level is filled before the sigma for this molecule. Okay, so that's B2, and then if we go to C2, carbon dicarbon, again, not a particularly stable molecule, but one that can be observed at least for short time scales. The orbital diagram is exactly the same as the previous one. So when the 2s mixes, they still give us our sigma and sigma star. And then when the two p's mix, they give us pi and sigma, but the pi comes first before the sigma bonding orbitals, and then the anti-bonding orbitals come in the same order. Okay, so that's the ordering of the orbitals, exactly the same. Again, the only difference between these ones and the others from the p block are the ordering of these two here. So when we have C2, each one has 4 valence electrons, so a total of 8 electrons that we have to put into this diagram. So we get 1, 2, 3, 4, 5, 6, 7, 8. All right, so we're just going to put those extra 2 electrons also into the pi level. We fill lowest to highest. So this molecule here is predicted to be diamagnetic. All the electrons are paired. The configuration is sigma 2s2, sigma star 2s2, and then this time our pi 2p is completely filled with 4 electrons. We can calculate the bond order. So out of our 8 electrons, how many of them are in bonding orbitals? 6. We have 2 down here and 4 more up here that are all in bonding orbitals. 2, 4, 6 of our 8 electrons. The other 2, the sigma star 2s, is still filled, so we have 2 electrons that are in anti-bonding orbitals. And so for this we predict a bond order of 2. All right, and again, something that's a little bit weird about molecular orbital theory that we wouldn't have gotten from valence bond theory. If the bond order is 2, that means this is a double bond. And as we said from valence bond theory, we would predict that a double bond would have 1 sigma and 1 pi. But if we look at the bonding in this molecule, again, the sigma and the sigma star 2s cancel out. So both of our bonds are going to be pi bonds. We only have the pi orbitals filled here. So it's a double bond, but it's going to be no sigma bonds and 2 pi bonds. Again, something that's not predicted from valence bond theory. All right, so we get 2 pi bonds in this molecule responsible for the bond order of 2. No sigma bonds in this case. Okay? And then finally, the last one in this series is N2. So N2 has the same ordering of orbitals. The 2s mixes to form sigma and sigma star. The two p's mix to form pi and sigma coming first, and then pi star and sigma star. All right, N2 has a total of 10 electrons. Each nitrogen is in group 5, so then each one has 5, and then we multiply that by 2 to get 10. All right, so 10 total valence electrons. When we fill up the diagram here, we get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this time we also fill the sigma 2p bonding orbitals. Nitrogen is predicted to be diamagnetic, and I think they showed it briefly in that video that I gave you last time. When you pour liquid nitrogen through a magnetic field, it goes straight through. It doesn't attract the magnetic field. So N2 is in fact diamagnetic, which the theory predicts. And if we calculate the bond order for this, if we were to draw the Lewis structure for N2, we get a triple bond to make sure that each one has a complete octet. And if we calculate the bond order from molecular orbital theory, we have 10 total electrons. 8 of them are in bonding orbitals. Sigma 2s, pi 2p has 4, sigma 2p has 2, so 2, 4, 6, 8 electrons are in bonding orbitals. And then the last 2, again, this filled sigma star 2s, we have 2 electrons that are still in the anti-bonding. And so we also predict a bond order of 3 or a triple bond from this theory as well. Okay? And in this case, it's what we would consider a normal triple bond. It's 1 sigma bond and 2 pi bonds, just like we would predict from valence bond theory. And the configuration, if we wanted to write that out in sort of the longhand form, is going to be sigma 2s, 2, sigma star 2s, 2, that's terrible. And then we have pi 2p 4, sigma 2p 2. So that's how the 10 electrons in N2 arrange themselves into the molecular orbitals. So all the antibonding ones up here are going to still be empty in the ground state. All right, so that's how we do all of the diatomics for the P block: B2, C2, N2, O2, F2, and neon 2. So we just write the diagrams with the orbitals in the correct order, and we just add the electrons in just the same as we would for atomic orbitals. Now, one little thing I want to tell you about molecular orbital theory is, for these neutral molecules, we always predict whole number bond orders. So we saw that O2 was a double bond, F2 was a single bond, B2 was a single bond, C2 was a double bond, N2 was a triple bond. All had bond orders of either 1, 2, or 3, but we can have fractional bond orders as well. Now, in this class, I think there's something in your book about it, but we're not going to have you do heterodiatomics, which is a diatomic that has 2 different atoms in it, but you can still get fractional bond orders if you have a charged species, like let's say N2+, which is called I think it's called the diazonium cation, if you want the name for it. So for N2+, we would still write the orbital diagram the same way we did for N2, but because of the positive charge, we have a different number of electrons. So anytime you're dealing with a charged species, you would still assume that the orbital diagram comes in the exact same order as the uncharged neutral molecule. So if it's N2+, we follow the orbital ordering for N2. If it was O2+ or O2-, for example, you would then follow the orbital ordering that we gave you for O2. So the ordering of the orbitals is determined by what the atoms are that are bonded together, but the charge then, of course, changes the number of electrons that we put into our diagram. So if we have N2+, we saw that N2 had 10 electrons, so N2+ would have 1 less than that, which is 9. So in this case, we're only going to put 9 electrons into our diagram. We have an odd number. So we get 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have a half-filled sigma 2p. And so the configuration is going to be sigma 2s2, sigma star 2s2, pi 2p4, sigma 2p1. We only have 1 electron in that last orbital. It's predicted to be paramagnetic. Remember, if we have even just 1 unpaired electron, it's considered paramagnetic. So there is an unpaired electron. There has to be if there's an odd number of electrons. And then finally, if we calculate the bond order for this one, 1/2, and then we count the electrons that are in bonding orbitals, we have 2 down here, 4 more up here, and then 1. So 2 plus 4 plus 1 is 7. This time we have 7 electrons in bonding orbitals. We still have these 2 that are anti-bonding. Those are always going to be filled for the P block. So we get a bond order of 2.5. Can't do math today. 2.5. 7 minus 2 is 5, times 1/2 is 2.5. All right, so again, we can predict fractional bond orders in the cases where we have odd number of electrons. Now you could also get a fractional bond order if you had, for example, NO, which has 11 electrons, but we're not going to do heterodiatomics. Even though they're very similar to these, but we're just not going to take that next step. All right, so what you need to be able to do then for these types of problems is write the orbitals in the correct order and fill them with the correct number of electrons, and then from there you can calculate bond order and number of unpaired electrons. That's really the level of depth that we're going to go with molecular orbital theory. Now there are a couple more things to then talk about in the context of MO theory, which is the idea of delocalization. So, for the detailed diagrams that I just gave you, we're only going to focus on 2 atoms bonded to each other. That's as complicated as we're going to get. But we do want to understand at least something about molecular orbital theory for more complex species, even though we're not going to draw the diagrams and all those things. So let's consider, this is an example your book gives that's a very good example of delocalization. And so, how do we treat the orbitals in a molecule where the pi electrons are delocalized? So we talked about delocalization a little bit when we talked about resonance. So we drew resonance structures for certain molecules like nitrate, where we have that double bond that can move around to different positions in the molecule. So basically that means the pi electrons are not localized in one spot. They're delocalized over the entire molecule. So how does molecular orbital theory account for that? So let's consider this molecule benzene. You guys will learn all about this if you take organic chemistry. So benzene is a hexagon of carbon atoms. So the formula is C6H6. Each carbon has 1 hydrogen on it. And as we already talked about in other contexts, carbon wants to have 4 bonds. It wants to have a complete octet with 4 total bonds. So to do that, we can draw alternating single and double bonds. So we put double bonds on alternating positions, and that's going to be then the structure of C6H6. But as you might recognize, I arbitrarily put the bonds here, here, and here, but why didn't I pick here, here, and here? So again, there's these 2 resonance forms that we can draw for C6H6, where we just put the double bonds in different positions. Where we could have put the double bonds here, here, here. All right, so this is an alternative resonance structure that's just as valid. It has still 4 bonds for every carbon, complete octets for everything. So these are the 2 resonance structures for benzene. So what that means is that these double bonds are not localized in one position. They're delocalized over the entire ring. So we have, again, a delocalized system where we don't have the pi electrons between 2 carbons. We have the pi electrons moving around between all 6 of the carbon atoms. So another way to draw this structure that you'll sometimes see is to indicate that these electrons are delocalized. Ran out of room there. There's our hydrogen. You'll sometimes see it with just a circle drawn in the middle to indicate that you have alternating single double bonds where the double bonds are delocalized around the entire ring. All right, so this is what the structure of benzene is. All of these carbon-carbon bonds, which are in between a single and a double bond, are equal in length. All right, so again, we don't have single and double bonds. We have bond orders of 1.5 for each of them. They're all the same. And all of the carbons, if we want to talk about the valence bond approach, are sp2 hybridized. All right, so for describing the bonding in molecules like this, we talked about there's valence bond theory, which is the approach of using hybridization and these localized orbitals on the central atoms that are then involved with the bonding to the other atoms. And then there's molecular orbital theory, which is the delocalized approach where all the orbitals are delocalized over the entire molecule. In some cases, and this is a very good example of that, it's useful to sort of use both bonding theories together to describe the bonding. So if we wanted to describe the sigma bonds in these molecules, remember that the sigma bonds are going to be formed involving hybrid orbitals. So each of these carbons we can think of as being sp2 hybridized, and those sp2 hybrid orbitals are going to be forming all the sigma bonds, because each carbon has a sigma bond to 2 other carbons and to hydrogen. So 3 sigma bonds for each carbon, and those 3 sigma bonds are going to be formed using sp2 orbitals. So if we want to draw sort of a picture of this, which is not going to be the easiest picture I've ever drawn, so I might mess this up before I get it right. We'll see. So each carbon is sp2 hybridized. Remember that the sp2 orbitals are oriented in the same plane 120 degrees apart. So for each carbon we have a set of 3 orbitals that sort of goes like this in a trigonal plane, 3 sp2 orbitals, and they're going to be overlapped then with an s orbital on hydrogen to make the CH bonds, and then they're going to also overlap with sp2 orbitals from the neighboring carbons to make the sigma bonds between the carbons. So we have another carbon here with its 3 sp2 orbitals. One of them forms a bond to hydrogen. We have another carbon here. All right, so all of these sp2 orbitals are going to be overlapped then to form bonds. So all of the sigma bonds then are going to be formed by overlapping these orbitals together. 1, 2, 3, 4. So I have one more to do. All right, I drew that roughly correct on the first try. All right, so basically the idea here is that each of these carbons, I'll highlight each carbon in red so the diagram doesn't become too confusing. So each carbon nucleus has 3 sp2 orbitals that are projecting from it, and those sp2 orbitals are going to be involved in forming sigma bonds. 2 of them form sigma bonds with neighboring carbons, and then one that points outside the ring is going to form a sigma bond with hydrogen by overlapping with the s orbital of hydrogen. So that's what the sigma bonding picture looks like in this molecule, and using the valence bond approach and hybridization is probably the most convenient way to describe it. All right, so just to write some important points about this. So the sigma bonds form by sp2 overlap for the CC bonds, or sp2 1s overlap for the CH bonds. All right, so again, this valence bond approach describes the sigma bonding, which has hybrid orbitals on carbon overlapping with other carbon hybrid orbitals and with atomic orbitals on hydrogen. Remember, hydrogen can't hybridize because it only has one orbital available for bonding. All right, so that's the sigma bonding in this ring-like structure. But then how do we describe the pi bonding? Because as I talked about when I first drew the structure of this, the pi bonds in benzene are delocalized. Remember, you don't have a pi bond that's just between these 2 carbons. You have a pi bond that sort of alternates around all of the carbons here. So the way we can draw the pi bonds, I reproduced a graphic from your textbook because this is hard for me to draw. But the idea here is that remember that if each carbon is sp2 hybridized, there's one additional unhybridized p orbital that's available for bonding. So remember that there's a total of 3 p orbitals on each carbon. 2 of them are hybridized, 1 of them is unhybridized in an sp2 hybridized case. So if we draw the benzene hexagon, sort of a side view of it in some sense, as best as I can. So each of these carbons here on the ring has an additional unhybridized p orbital that goes above and below the plane of the ring. So remember that the unhybridized p orbital is perpendicular to the plane of the sp2 orbitals, and so you get a p orbital that's going above and below the ring like that. And on each position you have a perpendicular p orbital above and below the ring. All right, and so what you get is you get pi overlap that's above the ring and below the ring for these p orbitals. All right, and that sort of then looks like this, where you get this delocalized pi electron density above and below the C6H6 plane. All right, now it's obviously a much more complicated picture than this, so we're not going to go through all the different energy levels, but if you have these 6 pi molecular orbitals mixing together, there's 6 p orbitals, 1 on each carbon, you can then form 6 molecular orbitals. And we're not going to go into that level of detail, but that's something you'll see if you take organic chemistry or other more advanced chemistry courses, which is that the 6 p orbitals in the benzene overlap to form 6 delocalized pi atomic orbitals. So we can think of the pi orbitals as being delocalized using the molecular orbital approach, which are formed by overlap or mixing of the 2pz atomic orbitals. All right, so if we assume that the plane of the molecule is xy, the 2pz orbitals are the ones that are unhybridized, and those are the ones that are available for the pi bonding, which is above and below the axis of the sigma bond. All right, so this sort of hopefully gives you an idea of how molecular orbital theory works in larger systems. We're not going to go into any more details than this on this topic, but the idea that if we have larger molecules, the molecular orbitals are delocalized over the entire molecule, and that's often a very useful way to describe bonding, especially when you have these resonance delocalization. All right, so that takes us to the end of Chapter 4. We'll start Chapter 5 on Friday.